Hi class, how y'all doing this afternoon? First of all, I want to apologize for missing class yesterday. Something came up I needed to take care of very desperately. And that might happen occasionally, but when that does, I've discovered the classes enjoy these little videos that I make. I was going to make another one, but I decided after a couple of questions some students had that I was going to make some discussions about the lab assignment. And I'll go into that kind of briefly. If you still have questions, please ask them, email them to me, or ask them by text. That's just fine. And we will also go over this in class on Monday. Now, I told you to do on Friday. I'm going to keep that due date and encourage you to get that in on time, at least over the weekend. But if something comes up and you think you made an error about that or something, that's fine. We'll turn it on Monday. So don't worry about that much. Okay, so I switched figures. So here's the actual lab itself. And the point of this, and we don't discuss blackbody radiation enough in classes in science because it's pretty important to us. But blackbody radiation, the cheap and dirty explanation for it really is that it's radiation that's generated within the object. Like everything generates blackbody radiation. I don't know where the name came from, and one day I'll look that up. But what it refers to is, since everything has some energy inside it, then the energy inside that object generates a temperature. That temperature will then translate into some frequency of radiation. Now, it just so happens that because our temperature, our body temperature, is about 98.6 degrees F, that generates a lot of infrared radiation. That's why night vision cameras work well on detecting people and objects like that. But the hotter something is, the more infrared it will generate. Now, that's not the only temperature that is generated. As we'll see here in this, the sun itself generates temperature. Now we have to go over some units, and I'm going to do that on Monday. But let's say that we know that 5,700 degrees Kelvin is very, very hot. Now the other thing we want to know about, we'll talk about, is I'm going to find it here in a second. The Earth's wavelength and frequency, and I forgot where it says this now. I should know this. Okay. The temperature, room temperature on the Earth, a nice 75 degree afternoon in the classroom, is the same thing as 300 degrees Kelvin. The temperature of the sun, the peak temperature of the sun, is about 5,700 degrees Kelvin. Now, that's important because now when I switch this, let's see if it works. Okay, here's the simulation itself that's come up, and I'll just show you a little bit how to work that. This is after you click on the simulation in the page on the experiment. You can then label the graphs. Boom, boom, boom. Now the sun is the number that we've been asked to find. They give a little bit different number here than you're asked to find. I'm not going to do that. I'm just because that'd be doing your work for you. Now, what I am going to do is show you this number here. This is about 3,000 degrees Kelvin. And this is the peak temperature of that. This is the peak temperature of a light bulb. And let's see if I can expand this. Yeah, whoa, too much. Still too much. Okay. So here is the black body radiation spectra, and black body radiation just fits this profile, but where it fits on this curve depends on its temperature. So we have visible radiation here. This is the stuff we would see in this case from the light bulb. But this is what's interesting about this over here. Its actual peak output, and these are arbitrary units. This says this is the highest peak. This is one whole unit is its highest peak. This is at a wavelength of 0.966 microns. And then this one is, we're not doing this for an assignment. So I'm just telling you how to do this to compare this. So this is the highest point. This is the wavelength of the peak of the light, the peak wavelength of the light, and this is the temperature at which it occurs. Now let's talk about the scale here, because this is kind of a weird scale and it's not well labeled. There is 3 microns. There is 2 microns, and there is 1 micron. So this number here this would be 0.5, 0.6, 0.7, 0.8, 0.9, and 0.966. That's where the peak intensity lies. This would be when we ask for the wavelength of the sun, we're looking for the peak intensity right here. Let's go back to this. Whoops. Wrong button. It's still the wrong button. I'll go back to that. So anyway, this is what you need to be looking for here for the graph you've got. And that's not what I want. There it is. Sorry about that. So if we adjust the temperature on the graph to 300 degrees, we'll get what the temperature is on a warm day. That will tell us the wavelength. We can then find out that will tell us the wavelength in microns. We can calculate the wavelength in meters. We calculate the frequency. This is the conversion factor right here. And we have some information in the back of the book that tells us how to convert frequency for a wavelength from regular numbers to scientific notation. And again, if you've got questions on that this time, I wasn't there yesterday to help you out, so we can perhaps go over that again. Oh. There it is. Sorry about that. I'm still figuring out how to use this thing. Okay, so there we are. That's some directions I hope helps you do the lab. And you can play with it for a while. I think you'll get familiar with it. It's not that terrible. And then see if you can answer the questions after that. And if you can't, email me or text me, and I'll try and help you out with the answers to the questions prior to class on Monday. So you can do that. I'm not too busy all weekend. It's too hot. So give me an email. I'll be happy to try and help you out. I hope this was kind of fun. Watch me poke numbers. And I will see you in class on Monday. Take care of yourself.